Fatigue corrosion and a case study on mid-air accident. Lecture by Dr.G.Subramanian, Chief Scientist Retired, CSIR Central Electrochemical Research Institute. Corrosion fatigue. It is the result of the combined action of an alternating or cyclic stresses and a corrosive environment. The fatigue process is thought to cause rupture of the protective passive film, upon which corrosion is accelerated. The corrosive environment can cause a faster crack growth. Otherwise, crack growth at a lower tension level than in dry air. Control of corrosion fatigue can be accomplished by either lowering the cyclic stresses or by various corrosion control measures. Fatigue fracture usually occurs at stresses below the yield point, but after many cyclic applications of the stress. The figure on the right side shows you number of fatigue cracks and pitting corrosion experience. Prevention of corrosion fatigue. Change design so as to reduce stress or cycling. Reduce stress by heat treatment for residual stress. Short pinning to change surface residual stresses into compressive. Use corrosion inhibitors with care. Use electrodeposited coatings of zinc, chromium, nickel and copper. Nitridite layers, that is heating of steels in contact with nitrogen containing material, example ammonia, sodium cyanide, etc. Now we are going to deal with a mid-air accident of an aircraft Aloha Airlines Flight 243 Boeing 737-200 happened on April 28, 1988 at Honolulu. Actually, the failure analysis report contains more than about 10,000 pages. For the listener's convenience, I have reduced it into only 16 slides. The miracle landing of Aloha Airlines Flight 243. You can see the video which runs in this link, following this link. The duration of video is about 8 minutes 51 seconds, which details about the incident. That is, it details the case study analysis of the whole incident. April 28, 1988. Flight 243 was scheduled for several island hopping flights. First officer conducted pre-flight inspection in darkness and noted nothing unusual. Airplane initially flew 3 round-trip flights from Honolulu to Hilo, Maui and Kauai. All flights were uneventful. No requirement for visual inspection between flights, and none were conducted. Accident flight departed Hilo at 1:25 p.m. with flight crew and 89 passengers on board. While leveling at inter-island cruise altitude of 24,000 feet, a portion of the forward fuselage separated from the airplane resulted in immediate depressurization. Captain assumed control, noting that airplane was rolling left and right and flight controls were loose. Captain noticed that the cockpit door was missing and he could see blue sky where the first class ceiling had been. Left engine failed. Restart attempts unsuccessful. Captain and first officer donned oxygen mask and initiated emergency descent. Successful landing in Honolulu Separated section extended from the cabin floor, equivalent to 1/4 of the fuselage length. One fatality, 7 serious injuries. The fatality was a flight attendant who had been standing at row 5 and was swept out of the cabin. A flight attendant at row 15 was thrown to the floor and slightly injured. Flight attendant at row 2 sustained serious injuries from flying debris. When depressurization occurred, all passengers were in their seats and seatbelt sign was already illuminated. Damage summary. At the time of the accident, the airplane had 89,680 flight cycles and 35,496 flight hours. After the accident, a passenger reported that as she boarded, she noticed a large vertical fuselage crack but did not mention it to anybody. Final damage consisted of the total loss of a major portion of the upper crown and damage to other structure in section 43. Damage were extended from the main entrance door aft about 18 feet. The meaning of aft is near, toward, or the tail of an aircraft. The airplane was determined to be damaged beyond repair and was dismantled on site. This is a pictorial depiction of the diagram of the airplane and the snaps of the plane while taking off and after landing. You can see the missing area. Section 43 of the flight has been missing in the mid-air. Accident was caused by pressurization related cyclic fatigue of fuselage lap joint. Disbonding of joint led to improper load distribution and fatigue cracking. Joint disbonding also led to corrosion, which contributed a joint failure. Lap joints in other locations had been the subject of ADs, that is Airworthiness Directiveness. That is a document issued, adopted by the agency which mandates actions to be performed on an aircraft to restore an acceptable level of safety when evidence shows that the safety level of this aircraft may otherwise be compromised. So, the lap joints in other locations had been the subject of Airworthiness Directive, but none in the areas of failure. Crack growth. When cracks form at the knife edges of the holes, cracks propagate from the hole edges. As cracks grow, they may link up. Over the time, this linking up of cracks can lead to catastrophic failure. Crack growth, a pictorial depiction of the typical crack growth and failure. The figure on left on the top gives you crack origin and knife edge, typical crack propagation. The figure on the top left bottom gives you typical fatigue crack location. You can see critical upper row of fasteners, outer or upper skin adhesive on both sides, and inner or lower skin stringer. You can see the fatigue crack location on the upper row of fasteners. The figure on the right side shows you 1, 2, 3, 4 depicts you clearly how the crack propagates and link up, which leads to catastrophic failure. Upper skin typical crack, critical rivet row, then it extends, it propagates. Figure 2, 3 and 4 shows it propagates and link up and leads to finally catastrophic failure. Lessons learned from this mid-air accident. Basic design and safety assumptions need to be validated. Routine maintenance and inspection may not assure detection of cracks and corrosion, which may lead to catastrophic failures. Safety assumptions had been based on the ability of these inspections to detect damage. Lessons learned. Continuation. Mandatory repair, modification, and replacement of principal structural elements. Requirement to develop directed corrosion inspection and prevention programs and mandate them. Review the adequacy of the structural supplemental inspection programs, enhancing and mandating them as necessary. Requirement to develop a limit of validity for WFD, widespread fatigue damage. Widespread fatigue damage in a structure is characterized by simultaneous presence of fatigue cracks at multiple points that are sufficient for development of cracks and major failures in the mid-air. So, requirement to develop a limit of validity for widespread fatigue damage and application in airlines maintenance programs. Assess the quality of structural repairs with respect to long-term operation. Develop regulations and guidelines for this assessment. Revisions to the 14 CFR, that is Code for Federal Regulations. Aloha's aircraft maintenance human factors lesson learned. Summary. Inspectors working under pressure. Inspections done at night, that is circadian rhythm upset for the human being involved in this operation. Inspectors suspended by safety harnesses. Required to inspect 1300 rivets. Documentation complicated and subject to interpretation. Engineering department was outsourced. Hangar lighting designed for DC-3s. DC-3s, the Douglas Commercial 3, was one of the most mass-produced, well-engineered aircraft in history. Built to last, to land anywhere, and never to break, Douglas churned out more than 11,000 of the type before and during World War II. Lack of adequate manpower, that is fatigue for 2 jobs. Lack of knowledge, just 2 hours of non-destructive training. Thank you very much for watching this video.